gosh, these smell good. Oh, so, hi. So what I have here, I've got some bowls of NAND gates. And the reason that I have bowls of NAND gates is that this is going to help us to talk about this idea of complexity. Complexity is going to be how we start to answer these questions that we asked about eval, like how many gates are going to be required to implement certain functions, and how can we tell when our eval circuit is going to be large enough for the functions that we care to implement, that sort of thing. Now, if you recall, there are sort of two main themes that we're going to be discussing throughout this semester. Those are computability and complexity. Computability is this question of what can a model of computing do. Complexity is how many resources are required to compute something under some model of computing. So we've already answered this computability question for Boolean circuits, which is to say that Boolean circuits are able to compute any finite function. So to tell whether or not some function can be computed by a Boolean circuit, we just have to know if it's a finite function. This complexity question, though, this is going to be the topic of this week's videos. So complexity is essentially going to be a property of a function, where it measures the number of resources that are required in order to implement that function. What we really mean by measure is the count of something. So whenever we look at the complexity of a function, we're going to say, what is the count of a certain resource that we might use while implementing that function? And what resource you actually decide to count is going to depend on your application and on your model of computing. So for example, with Boolean circuits, if we looked at NAND circuits, then our resource might be NAND gates. So to determine the complexity of some function, we're actually going to be counting the number of NAND gates required to implement that function in its most efficient implementation. If our model of computing was and or not instead, then we're going to be counting the number of collectively and or not gates that are going to be required to implement that. And now, anything that you could consider some sort of expensive resource, that actually makes sense to count as this potential complexity measure. So if we had a different model of computing, then we could say something like time is going to be our complexity measure, where we might have some definition for what time means in our model of computing, so we can count that in order to determine the time complexity of our function. We could also consider things like communication. So let's say that we had two parties who were on opposite sides of the country, and they wanted to compute something with their data. Then we could say that the complexity of that computation might be the minimum number of bits that they need to communicate over the internet in order to do that. So there are lots of options for what we could consider to be complexity. In all of these options, they have the same theme, which is that you are actually counting something. So now, something that we like to do with this definition of complexity is talk about things called complexity classes. So complexity classes are essentially organizing functions according to their complexity measure, so that we can group together all of the functions that use, say, a similar amount of resources. And these can be really useful if we wanted to, say, compare the hardness of different functions. So we know that some functions are harder than others, but what do we mean when we say harder? So with complexity classes, we could say, well, function f is going to be harder than function g because f has higher complexity, meaning it requires more NAND gates, for instance. So by being able to now compare the hardness of different functions, that's going to allow us to do things like, say, as I am trying to pick the size of my eval circuit, how big should it be, and what functions am I able to compute versus unable to compute once I have made that decision? So what's the cost-benefit analysis of picking my eval circuit size? It also allows me to sort of check the efficiency of my implementations of things. If I implemented some function and I used 50 gates, but I knew it belonged to the complexity class to indicate it only required 25 gates, then I knew I didn't have a very efficient implementation of that function. I should be able to do better than that. so I could work on improving that circuit. So for now, as we look at our complexity measures, we're going to be considering our complexity as the count of gates, the number of gates that are going to be required. As we progress through the semester, this idea of complexity is going to come up more and more. And when we have different models of computing, we're going to be looking at different resources, so be prepared for that.